Hi guys, it's Mick Swain. Um, just wanted to go over some of our notes on the history of the periodic table as well as the organization of the periodic table. I already shared this PowerPoint with you, but I decided, hey, why don't I try a voiceover? So let's go ahead and get started. So Mendeleev, Dmitry Mendeleev. I'm not sure if you've heard his name yet. He is the first to be accredited with the periodic table. He and another guy had published similar classifications of elements. However, Mendeleev was able to organize them based on properties, and he kind of like grouped them in categories and saw a trend going along in these periods. So we'll talk about groups versus periods in a little bit. But what he knew of that day, he left open spots saying, hey, I think something's missing. I'm looking at all of these trends. This is what I have going on right now. And there's something here that's missing. So he kind of predicted unknown elements and their characteristics. So that's great. So he realized that the physical and chemical properties of elements were related to their mass in a periodic way. What periodic way means is that there's a trend. So every period that repeats, so as we're going left to right, every period, the pattern repeats itself. So kind of how we have like our lithium and then our sodium, they're in the same family, but they're in different periods. They exhibit similar characteristics. He then arranged them in groups with their similar properties. They fell into vertical columns. The vertical columns of up and down, those are our groups or families. And we've already talked a little bit about how the same group, the elements have the same number of valence electrons. So column 1 has 1 valence electron in its outer shell. Then we move into column 2, 2 valence electrons in their outer shell. We skip the transition metals, that big chunk in the middle, and we go to column 13. They have 3 valence electrons in their shell. So he didn't exactly know all of this, but he knew that they had similar properties. So that's why he put them in the same group. So here's our lovely stuff. One thing though, he didn't know about the noble gases back then. So he didn't actually have those in his periodic table. All right, so again, I mentioned the gaps. So he did leave gaps in his periods. That's because he knew that there's something missing. All right, so he was able to predict their relative mass and their properties. So it says here, for example, he predicted the properties of an undiscovered element that should be below aluminum on his table. And then the element called gallium was discovered later down the road. The properties were really close to what Mendeleev had predicted. All right, Henry Moseley came in later, and he took Mendeleev's periodic table, and he took all the information that they had learned in that time period. And he said, so we know now about protons within the nucleus. So every element has their unique atomic number. Let's go ahead and take that similar organization, and we will organize it by atomic number instead of atomic mass, because Mendeleev had organized it by the mass. Well, here Moseley said, now that we know about the atomic number, let's go ahead and organize it as such. Our current periodic table starts at 1, right? It starts at hydrogen. It goes in order of atomic number. So 1, then we skip all the way to helium, 2, and then the next row starts with 3, lithium, and then all the way to our neon, and then we just keep going. But they still kept their groups, those columns, as similar properties. There's no more gaps as of right now, right? So we've had many different things discovered. We have 118 currently discovered, but there could be more. You never know. We only know what we have in our knowledge bank right now, right? So there's more discoveries. You never know. We'll find out. 98 of our current 118 that we have discovered occur naturally. I know this is kind of like, whoa, what is this? This is our periodic table. And we see that there are different colors going up and down. This tries to signify, hey, groups, aka families, are in the vertical columns. So here we have column 1. Those we're going to talk about soon. Alkali metals. Each group, family, column has a specific name. Except here we have this big chunk in the middle. We group those together and we call them the transition metals. Notice we have similar image, except now the colors are going left to right, left to right. This is showing us that as we go left to right, we have what we call periods. So the new colors represent a new period. New periods means we have more energy levels or shells or orbitals in which we put our electrons. Elements and periods do not have similar properties. They just have similar energy levels. All right, here we see a little bit of different shading, and we've organized them by metals, nonmetals, metalloids. So as we see here, we have the metals. Metals take up the majority of the periodic table. There's this kind of divider here. That's the metalloids. And then on the right-hand side, we will see the non-metals. Metalloids, the staircase here, you'll hear us say the word staircase a lot. Those metalloids have properties of both metals and of nonmetals, but they are here and they kind of separate them in our categories. But we will notice that we do have one nonmetal on the left-hand side, and that is our hydrogen. All right, so properties of metals. Notice we have a variety of metals here, some information on them. Metals will lose their valence electrons. When they lose their valence electrons by giving them to another element when they form a bond, they now will have a positively charged ion because they got rid of some of the negative electrons they had in their outer shell. Metals are typically solid at room temperature. However, we do have the outlier of mercury. Mercury is a liquid at room temp. Metals exude luster. They're shiny. That's what that means. They are ductile, so we can roll them kind of into a wire. So you can see here, we can make copper wire. I've seen a variety of different wires going around. Malleable, so we can hammer them into sheets. So here we see our aluminum foil. You guys saw my tin sheet in the classroom, and we noticed how easy some of it was to kind of like cut into. That was, different metals have different properties. They have high melting points. It's going to take a lot to melt them down. That's why we use them in like our pots and our pans so that we can heat the food up, but without, ruining our lovely dishware. And then they're dense and they're great conductors of heat and electricity. All right, properties of nonmetals. So here we see a variety of different nonmetals here. They will welcome electrons from other elements because they want to fill their outer shell since they're really close to filling it. So as they accept these electrons, they then have a negatively charged ion that we call anions. Different nonmetals exist in different states. So we have bromine exists as a liquid. We have sulfur as our solid. We have nitrogen gas, oxygen gas. We have the noble gases, so helium, and neon, and argon. But they're dull, they're brittle, they're poor conductors of heat and electricity, and they typically have lower densities. If we think of gases, they are able to flow. I think of like helium, that's less dense than the air. That's why that if you fill a balloon up, it'll float, etc. Metalloids exhibit properties of both metals and of nonmetals. These are just some of the examples I was able to find of what they look like out there. They can be shiny, but they can also be dull. They are semiconductors, so some of them, we use in different items so that we can conduct heat, but they're not the best, so they are used though. And they're brittle, they break also, and some are malleable, but others are not.